Okay, hello and welcome everyone today to today's Section J case study. My name is Tom Symons. I'm an ESD consultant at SUHO, and hopefully we're looking to, I suppose, explain some of the things we've gone through in the previous Section J webinars, which you can find on our YouTube channel, and just provide a bit more detail about how we do a DTS assessment. Obviously, for starters, it's worthwhile working out what exactly the DTS sort of stands for. So the deemed to satisfy pathway is where we assess each of the building fabric elements. That's the roof, the wall, the glazing, the floors, etc. And each is required to comply on its own merit. So this is traditionally a cheaper assessment cost, but pretty much always a higher build cost. Now, if we look at the performance pathway, which is the other pathway, that's the JV3 method, which was very popular for 2016. It's a more holistic approach undertaken by modeling a proposed building, and then we convert that proposed building to a reference building. As long as the proposed building produces less greenhouse emissions than the reference model, then it complies. Now, this is always going to be a higher assessment cost, but traditionally also a cheaper build cost. It allows more flexibility in your design and how you insulate your building, where you put it, and the glazing requirements for it. Today we'll focus mainly on the DTS assessment and hopefully share a bit more information about it and how we assess it. So in terms of the key areas of change, you've probably seen this slide on my previous webinars. The building envelope, as we move toward transition towards obviously hopefully achieving sort of net zero buildings. This code change is targeted about a 30% improvement, and we're looking to sort of improve that by about 7 to 10% for the building envelope, and the remainder is made up of lighting and HVAC efficiency improvements. Today we'll focus mainly on the building envelope side of things and how that's changed. So if you've watched the previous examples, we've gone through how a couple of school buildings and what the requirements were. Hopefully today we'll be able to sort of explain how we've come to those numbers and how you could achieve compliance in doing that. So we'll break down each of these sections. The school building we're talking about is a single-story classroom building. It's class 9B, so it's daytime operating. Daytime operating isn't actually something that's mentioned in the code, but it's, I guess, a simple way to understand what the class is. It's in climate zone 5. The climate zone is always important for any assessment. It adjusts like certain R value requirements and that sort of thing. Also greatly impacts the facade calculator. It's concrete slab on ground. There's 35% glazing to the north, east and south. And importantly, all the glazing is well shaded by sort of 3 to 4 meters of shading. So which you can see around the perimeter here. Always important when you're doing a Section J assessment to define the envelope. That's the thermal envelope in this case that we're talking about, and the code defines it as the parts of a building fabric that separate a conditioned space or habitable room from the exterior of the building. That's easy, that's an external wall, say, but it's also separating it from a non-conditioned space, such as a plant room. Maybe you have a warehouse tacked on at the back of an office space, or you might have, say, a basement car park underneath a building. In this case, our envelope's relatively easy. It's the roof/ceiling, the external walls, and the concrete slab on ground. One of the big changes for this code change was the wall and glazing being combined as a facade calculation. That's now that we're treating it as one system, which is obviously sort of common sense. It's an upgrade for our commercial code for Australia, but it's certainly something that's been done around the world for years. You've got 2 methods of calculation for this. You've got method 1, which is per orientation. So that's considering it in north, east, south, and west orientations. Or you can also use the method 2, which is a combined calculation. That gives you a more balanced result for your requirements. I would expect most clients would probably prefer to use method 2 because of this, because if you're familiar with the 2016 glazing calculator, it tended to be that you had some orientations that were quite stringent and others that were more lenient. Method 2 will give you that balanced result so that you're not stuck with some facades having to have relatively tight requirements. This is important, and part of the wall and glazing being considered as one system is that there's now new total system U values that have been introduced. And the point of that is that we're considering the whole facade having to achieve that total system U value. Now, for those of you who are unfamiliar with the U value, it's the inverse of an R value. So for most daytime operating buildings, the U value requirement is a U value of 2, which is equivalent to an R value of R.5. So it's not something that's too crazy, but it's the fact that you've got glazing, which traditionally doesn't perform very well at all, particularly in Australian glass, which might be sort of between a U value of 3 and a U value of 7 on the really cheap single glazed units. So when you convert that to an R value, you're looking at an R value between sort of 0.15 and 0.3 or something like that. And so when you combine both the walls and the glazing into one, we're targeting that total system U value of 2 for daytime operating buildings, which this classroom building is. Now, to achieve compliance, we've spent a lot of time developing our own facade calculator. Obviously, there's a picture on the right-hand side of the screen, which is the ABCB's facade calculator, the download page. It took a long time for the ABCB to sort of finally release this. It was released the last week before the code change. And now, in the end, we decided to develop our own at SUHO so that we could obviously have a greater control over how it was developed, how we could input stuff quickly and more efficiently, but also it's given us a great understanding of how it works. So the way we've set ours up is we have to achieve a required wall R value, which is to the code, and then it will put out a maximum performance requirements for the glazing, which is the U value and solar heat gain requirement. In terms of the wall R value requirements, which is that initial requirement, there's a bit of an interesting tipping point in the code. Wall R values are based on the glazing percentage. So if you've got more than 20% glass, the code is considering that you're going to have to, well, glazing is your key driver in how the facade performs. So that means that the walls are actually only required to achieve R1, but yeah, as the glazing is as I said, the key driver. If you've got 20% glazing or less, then daytime operating buildings have R value requirements of about R1.4 for climate zones 2 to 8, R2.4 for climate zone 1, which is a bit of an anomaly, I suppose. Then nighttime operating buildings, which are classes 3, 9A and 9C, places where people will stay overnight, have higher wall R value requirements, anywhere up to R3.3. So this is something that's a lot more stringent, and as we'll touch on thermal bridging in a second, walls achieving R3.3 is actually relatively not impossible, but it's much more difficult. So we'll touch on the thermal bridging calculations now. Thermal bridging has finally been introduced into the commercial code, yet to be introduced into the residential code. It's something that people at Passive House take very seriously. We're factoring in how insulation that's got framing members, such as in roofs, walls or floors, how that framing member is bridging the insulation. So it's typical in a stud wall if you've got insulation batts between it, if you've got ceiling joists which have got ceiling batts in between them, or if you've got you're intending to put insulation between them, any of those situations, the insulation layer is going to be bridged, and that's going to mean it performs much less effectively, generally, than how it would if it wasn't bridged. So in terms of Section J compliance for fabrics, we're calculating each of the layers of a construction. So in a simple wall, say, We've got our external air film, our external cladding. We've got a bridged layer, which is going to be calculated to the New Zealand standard 4214. Then we've got an internal lining and internal air film. For reporting, we're reporting to AS 4859.2, which is the Australian standard for thermal performance of insulation, and a full breakdown of your construction should be tabled, which demonstrates to both the client and also the project's building surveyor or certifier as to how we've achieved those total system R values. Just touching on so we'll use a super simple wall construction here just to make it really easy to explain, I suppose. For this particular classroom building, we'll assume that it's got a very simple fibre cement clad wall. It's got a bridged layer of our 2.5 insulation bridged by a steel frame or steel or timber frame. We'll use both examples to demonstrate how they perform differently. A 10mm plasterboard lining, and then you've got your external air film and your internal air film on the inside. Now, the New Zealand standard 4214 is the isothermal planes method for calculating thermal bridging. That means that we consider each of the layers that are continuous, as we did for 2016. We calculate, or we add up the external air film, which will achieve 0.04. We've got our fibre cement sheet layer, which doesn't perform particularly well, but will give us some R value. Then we've got our bridged layer, and in our bridged layer, we do effectively an area weighted average using the isothermal planes method based on the New Zealand standard. That calculates the effective R value of that layer. Then we've got our continuous 10mm plasterboard lining, which we add up as we would have done for 2016, and our internal air film. Now for this wall construction, I've assumed a 2.7 wall height, relatively standard stud spacing of 450mm with 1350 noggin spacings. It's important that if anyone's doing your Section J assessments, they're going to have to know your framing details, because at the end of the day, unfortunately now, it's no longer really a guessing game. To do it properly, you actually have to understand these numbers and be able to input them into whichever calculator you happen to be using. A quick example of how this bridge layer performs. So what's better, timber or steel? For 2016 code, if we're going DTS, the R2.5 insulation bat in that layer achieved R2.5. It was really easy. I suppose DTS was something that architects could do themselves, just quickly back of house, because it wasn't something particularly complicated and you didn't really need to spend much time understanding the calculations. For NCC19, timber stud frames using those same framing details on the previous slide will achieve about R1.8. And importantly, if it's metal stud, it will achieve about R.8. So you can see that the difference between 2016 and 2019 of actually considering the actual effective R value as opposed to just, I guess, a very crude understanding of the R value from 2016 means that we're actually starting to factor this in properly. Now, the isothermal planes bridging calculation is relatively simple. It's, I suppose, well, very simplified in terms of it's only one-dimensional. It's not really factoring exactly how the bridging is performing, and it also doesn't include things like point bridging or bridging from fasteners and stuff like that, which some of the other standards do consider, but it is a start, at least for the Australian industry. In terms of one question that we've received a lot in the last few months since we've taken on 2019 and been assisting our clients work through it is, can I add more bulk insulation? At the end of the day, I suppose one of the key things to know is that steel frames are still okay. We just actually have to understand how to treat them, and that continuous insulation is key. So adding more insulation as bulk insulation in between frames actually has very little impact. And as you can see that in the example at the bottom of the screen here. If we consider a metal frame, which was the same as the one on the previous page, that was 90-35 framing members at 450 centers. R2 was achieving about 0.7, And then if we've got R2.73, if we bump that up to R2.5, it'll achieve about 0.78. So you can see that it's really not making any difference. At the end of the day, we have to start considering about continuous insulation and using that to be able to achieve the R values that we require. This example, although talking about a wall in this situation, is exactly the same. So I've had a similar issue with, I suppose, some of our modular clients who obviously have lightweight frames and generally prefer to put insulation between joists as opposed to underneath the side of them. That's completely understandable from a transport point of view and stuff like that, but from a how the fabric is actually performing point of view, for energy efficiency, you can see that the only way to really increase that R value is to actually start adding thermal breaks, or even better, continuous insulation. Just saw a comment from Noy. Is thermal bridging in NCC limited to framing members? Yes, it is, Noy. Were you referring to bridging by windows and that sort of thing, or fasteners? Feel free to add another comment, but yeah, in this case, generally we're only considering framing members within walls, floors, roofs, or ceilings. So back to our example, if we add up all of our R values to work out what the total system R value of that fabric is, we've got our external airframe, which achieves a relatively minor 0.04. We've got our 8mm fiber cement cladding. We've got our bridged layer, which was R2.5 insulation batts in a metal frame in this case, and we've included the thermal break tape to achieve R1.39. That's obviously less than what it did for 2016, but the thermal break tape is assisting that metal frame in performing slightly better. Then we've got our 10mm plasterboard lining and our internal air film, and that total adds up to an achieved R value of R1.64. Now, I suppose there's probably a bit of a debate in the building sort of sciences area as to if a thermal break should be sort of a tape or if it should be a continuous layer. If you consider the fact that a continuous layer is actually going to stop horizontal heat transfer as well, then it makes a lot more sense for it to be continuous as opposed to a thermal break tape, which the heat transfer is likely sort of just going to deviate around that thermal break layer or tape. But the NZ standard does say that we can include just a tape. So if we're considering it in single one-dimensional heat transfer, which obviously isn't real, but if we are considering that, then it is acceptable. In terms of, so that brought us to the end of the wall calculation. That achieved 1.64, and now we can add it back into our facade calculation for the glazing requirements. So the way we've set up our calculator is to give us what the maximum requirements are for the glazing. So that means that we factor in both for method 1 or method 2. We've got our minimum wall R value requirement, which in this case for method 1, there's one orientation on this design that doesn't have any glazing on it. That means that we hit that tipping point where we've got less than 20% glass and we have to achieve the higher wall R value. So we have to achieve R1.4 on one of the orientations. In this case, I've kept it simple and just applied that same wall to all of the orientations. So we're achieving 1.64, and that gives us our glazing U value requirements of sort of a higher performance single glazed unit. We've then also got our method 2 result, which, because overall we've got greater than 20% glass when we combine all of the external facades, that means we've got an R value requirement of R1, and we've our R value of 1.64, and then calculate what our combined glazing U value requirement is, which in this case is 4.5. Now, we've also calculated our solar heat gain requirements for the external glazing. In this case, it's not impacted by, well, as always, it's not impacted by the wall R value requirement or the glazing U value requirement. it's purely based on the external glazing percentage, the external facades, and also the amount of shading that we've got over those layers, or over that glazing, sorry. So here you can see that there is, again, we've got that balanced result for method 2, which gives the sort of more average solar heat gain requirement. Yeah. A couple of last points on the facade calculation. So the glazing U value and wall R value are in balance. So that means that if we say we decide that, in this case it's not really that obvious, but say this was sort of more around the back end of double glazing, pushing on single glazing, maybe a client might would prefer to go high performance single glazing instead, then increasing the wall R value will give a slightly greater U value allowance. Importantly, if the window solar heat gain is a little bit low hypothetically, then either reducing the amount of external glazing or adding additional shading will allow you to do that. Importantly, any glazing values that we mentioned in a SUHO report, or really anyone in the industry as an ESD consultant is mentioning, should be referring to combined frame and glass values. So that's AFRC values, which you can also find on WERS to give you an indication. Yeah, going back to noise question in the comments, in terms of geometric thermal bridges, like corners of buildings, we're at this stage not really focusing to that level of detail. It's still very general, as in full facades of a wall type, a ceiling type, a floor type, that sort of thing. And also not touching on things like where hypothetically you might have a concrete floor that is exposed on the outside and effectively allowing heat transfer through, which apparently does have pretty big impacts in terms of thermal bridging as well. Touching on the roof compliance, for NCC 2019, the J1.3 requirements for roofs weren't too much of an update really. They were pretty similar, but again, we're remembering that we're factoring in thermal bridging, and that means that these R values do become slightly harder to achieve. So for climate zones 1 to 5, it's R3.7, which is most capital cities. For climate zone 6, it's R3.2. And in this case, we're in climate zone 5, so we're trying to achieve R3.7 downwards. The downwards is important to mention because you achieve different R values based on if it's summer or winter. For roofs, in this case, we're looking at downwards, which is for most roofs, it's downwards. That's an R summer value. For your floors, in this case, we'll be going for an R winter value, which is downwards as well. In terms of the roof color requirement, there's an increase in stringency around that. So now if we're going DTS, you're required to use light colored roofs, which is a solar absorptance of less than 0.45. That's limiting you to the 5 COLORBOND colors that you can see on the screen here. And importantly, it also excludes zinc aluminum colored roof sheeting as well. In terms of the roof R value calculation, I kept this relatively simple just to summarize, I suppose. We'll assume that the roof has a relatively standard, just pitched roof with a flat ceiling. We'd be considering an external air film, the steel sheet, which has very little R value, just about nothing. We've got a R1.8 reflective roof blanket, which is compressed to the purlins. So that has an effective R value of about R1.4, and that's because we haven't included roof spaces in here. The roof blanket's been compressed over those purlins. We've got a reflective airspace, a bridged R2.5 insulation bat, bridged by a metal frame, which is obviously going to be factoring in the bridging calculation as per New Zealand standard 4214. We've got a 10mm plasterboard lining and then the internal air film. Now, as I mentioned, we've factored in both the compression of the roof blanket and the bridged insulation bats, trying to, I guess, get a more exact R value of how it's going to perform. Obviously, as we've touched on, it's not a complete representation, but we're getting closer to that, at least a step in the right direction, closer to that point. So the total system R value would achieve approximately R1.4, and that would pass having to require the R3.7, which we mentioned on this slide. For the floor compliance, for 2019, most of the floors are still required to achieve R2. The interesting addition to this was that concrete slab on ground in climate zones 1 to 6 now are also included in that requirement. Previously, it was only climate zones 7 and 8 that required slab insulation. And the interesting thing here is that there's that tipping point. So, which we'll touch on in a second, which is based on the soil resistance calculation. As I mentioned earlier, or just on a couple of slides ago, again, we've got upwards and downwards heat flow directions. So in this case, we've got upwards heat flow direction, which is our summer, and downwards heat flow direction, which is our winter. And in this case, we're targeting a downwards heat flow direction, achieving R2. So specification J1.6 gives for concrete slab on ground, gives a soil contact resistance value. That's an effective R value based on the fact that the slab is in contact with the ground, and that provides a certain resistance. So in our example, our floor area was approximately 625 square meters. Our external perimeter was 110 meters, and then our walls are approximately 100 mil thick. Obviously in real life, they're probably going to be a bit thicker than that, but for our simple solution, they're 100 mil. So that means that we achieve an effective R value. Our ratio of floor area to perimeter is approximately 5.6-ish, and that puts us at an R value of around R2 with 100 mil thick walls. The fact that the concrete slab on ground through the soil resistance achieves that R value means that we do pass the R2 requirement, achieving about R2.3. To calculate that, we've considered the internal air film, the carpet floor lining, 100 mil concrete slab, and also the soil resistance R value. Another thing that comes up a little bit is what's the R value of concrete. Concrete has a pretty poor R value. 100 mil concrete slab is probably about R0.1. So increasing the slab thickness isn't really going to help you to achieve R2 unless, well, no, it's generally not going to help you achieve R2. And so if you using the calculation, like the table that we showed you just before, it's relatively easy to sort of check if you'll require some level of under slab insulation. And I suppose that brings us to sort of the key tipping points between DTS and JV3. DTS is the quicker solution to compliance generally, as long as you've got a fully documented project, or you can advise us what your framing details are and what all your fabric details are, then it's definitely going to be quicker to do a DTS solution, both in terms of timeline and also in terms of compliance cost. However, sometimes JV3 is really the only solution for you to achieve compliance, and so if you've got, or if the client has to have a darker roof than that 0.45 solar absorptance, if you have minimal shading or and end up with a tight external glazing solar heat gain requirement, that's certainly likely if you have a lot of glazing and don't have very much in the way of eaves or verandas or that sort of thing. And if your slab is less than about 400 square meters, dependent on the external perimeter ratio to floor area, then there is a risk that you'll require under slab insulation, which wasn't previously the case for climate zones 1 to 6. The interesting thing about the slab insulation is that so far from our modelling, generally we've found that adding slab insulation to daytime operating buildings actually makes the reference building perform worse, which is ironic. Obviously the code's trying to improve insulation levels in the expectation that it's going to improve energy efficiency, but sometimes in daytime operating buildings it doesn't show up at all, and sometimes makes the reference building perform worse, which actually helps you achieve a pass for JV3. So if any of those things, that's roof color, if you've got a lot of glazing, generally if you send through a set of plans and elevations, we can look at it relatively quickly and tell you if the solid heat gain requirement is going to be pretty tight, or if the slab area, again, also happy to quickly do that calculation for you to work out if you're likely to need under slab insulation. That generally directs which pathway to compliance is the best option. JV3 is the more cost effective and more time consuming, but it does allow that more flexible solution. So quickly touching on what we need as consultants for a DTS solution. To give you a quote, we'll need floor plans, elevations, the building's class is always important, and conditioned areas. The building's class is important, as we touched on earlier, because things like wall R values can become quite stringent depending on if it's daytime or nighttime operating. Of course, which code, if it's NCC 2016 or 2019, is going to be important. Most projects now are going through as 2019, but we are still seeing some go through as 2016. So if you haven't worked that out yet on a project that's been around for a while, please get in touch with your building surveyor or certifier, because the sooner you work that out, I guess, the less surprise there is going to be further down the track, particularly if costs are suddenly driven up. To assess the building, we probably do need a few more details. That's things like, obviously, floor plans, elevations. We'll need more in terms of sections and details, particularly around your framing details in terms of the sizes and spacings. And that brings me to the end of the presentation. If you have any questions, please feel free to add them to the chat. If not, also feel free, if you need any advice, feel free to get in contact. We're more than happy to discuss projects that you might have on the go. If you just need some general advice around NCC 2019, happy to help. Thanks for joining us today.